Well, thank you, Bob. And I want to say thank you very much for inviting me and being here to present to you folks today and talk to you today, and among the other speakers. And I think the theme of today's, the whole purpose of our seminar is, as Bob mentioned, we have to deal with disruptive technologies. But the more you understand about what we're dealing with and how to deal with it, which is what today's speakers will bring to the forefront, the less disruptive they are, the less scary they are. So call them disruptive technologies, bleeding edge, whatever you want. They can be dealt with. And ITM, we do consulting. Just as a brief, I believe the intros were handed out, so I don't have to give you anything. You can always look at our website. But understand we do things like process audits. But we also do what we call process failure analysis, which is troubleshooting, fancy word for troubleshooting. We just didn't like using troubleshooting. Sounds like the Maytag repairman or something. So, but that's what we do. We're the field, if you will, the on-site reciprocal of, say, an FA lab or something along those lines, where we go out and try to figure out what's going on and what's going wrong. And of course, of recent, a lot of the areas we've come out to, been brought out to mitigate have to do with bottom terminated components. And I also, as I was telling the guys last night, I am right in the middle of making a move. After 27 years in the tropics of New Hampshire, I am in the process of relocating to Tennessee. And I hadn't moved, like I said, 27 years since I moved there from California. And so my office, or ITM's intergalactic headquarters, as we like to call it, you go cleaning out and you find stuff you just can't believe. I mean, you talk about, we're talking about anachronisms. And one of the things I found last night, well, a couple nights ago, was an 8-inch floppy disk. Wow. So it was right between my fax machine and my beeper. And I carbon dated it, and I figured it was probably from about 1978 when I worked for Universal Instruments, and the machines were transitioning from NC Control to, we were using the DEC PDP 1104s. And it's big, fat floppy disks, and it's just amazing. But it's typical what we've seen with, certainly with memory, everything. We've seen the same theme: cheaper, faster, smaller, hopefully better. And so what we're seeing, of course, we've seen that trend. We all know it all too well. We all have the battle scars. But that's exactly what's been happening with component technology. So one of the evolutions, of course, has been the bottom terminated component, as it's officially called. But of course, there's a lot of other names, and and other forms, different forms of it. But the IPC 7093 has agreed that they're going to be called bottom terminated components. And but again, some of these, and the other thing we see in our industry is everything old is new again. It's a reoccurring theme. If you go back 30 years plus, we had what we call leadless ceramic chip carriers, and it's basically, if you will, a bottom terminated component in a different form. They were ceramic back then, but and they still exist. So again, things kind of rise to the forefront again. I'll throw another trivia at you. Does anybody know where the idea of the ball grid array came from? Who basically invented it, if you will, and when? Anyone want to take a shot at it? IBM. IBM. Okay, when? 1965. Believe it or not, they were doing I think it was a resistor network, and they had, for some reason, I don't remember why, but on their MST cards, they had to use a collapsible ball. They came up with using this collapsible ball technique. So they're actually credited with it. And by the way, anybody ever ask you a rhetorical question, do you remember when? The first answer, always say IBM. That doesn't work, try Bell Labs. And usually you're going to hit it right when that is. And usually around 1964, 65. Say the same thing about conductive epoxies. Let's see, that was IBM about 1965. Yes, it was, and working with Sheldon. So anyway, but everything old is new again. And we find new purpose and things along those lines. So these are just some of the other names you've heard of. QFNs is a very common one. We're going to look at some of these land grid arrays and QLPs and BLTs. I'm going to go for a BLT about now. And so IPC 7093 was released 2001. Despite my little cartoon here, it really is a very good specification. The guys really did a good job writing it, and I'm not going to say it makes great, reading, but it works for him. But basically, it kind of uniformed things. So, again, everything has its silver lining. So as much as we go, oh God, how are we going to deal with these damn things? Or other people say, hey, these look real easy to deal with. The bottom line is that there are some advantages to this. First of all, from a thermal standpoint, again, wood soldered, you have a contact ground pad. And again, that's always been one of the issues as our processors got faster and faster and more powerful, as well as other components, was heat dissipation. Remember that a lot of leads, a lot of the standard components, balls and ball grid arrays, leads and leaded components, a lot of those were not only for electrical connection and obviously in surface mount mechanical, some were for heat dissipation as well. So now we have this wonderful thing for ground contact pad. However, this is of course one of the nemesis, as we well know, of working with this component, particularly in terms of voiding. You also basically have an exposed copper die pad technology incorporated in a lot of those too. You basically, again, with this type of thing, you have a stable ground connection. Size-wise, in horizontal area and vertical, it's not the smallest of a device. Obviously, flip chip is, and chip scale is typically smaller, though some of these are in the area of chip scale. But it presents a very, very small, both horizontal area and also vertical. You know, the profile is very short. Weight, of course, they're very low. Again, not as much as a flip chip, because a flip chip doesn't have external packaging, but there's other advantages, for example, you know, with regard to underfill and things along those lines. And in performance, we're typically talking about very low resistance and capacitance from a parasitic standpoint, because there are no leads typically acting as antennas, which we see on a lot of different devices. And we have reduced lead inductance, and this seems to be very advantageous in the 2 to 10 gigahertz range. So a lot of the microwave and ultra-high frequency applications. The other advantages is this fairly simplified construction, putting these things together compared to other types of components. Fairly easy PCB trace routing, because we have perimeter I/O pads on most of these, as opposed to a grid that we see on a lot of area arrays. So we're doing that. And right now it is considered the lowest cost package. Approximate last estimate we saw was about, you know, something of a half a cent per pin, something along those lines. And then the other area where, you know, again, and we'll be hearing, I'm sure Greg's going to be talking about this big time, reasonable yield and reliability. Well, depends, it all depends on the application. But as I said, this is just another part of the evolution that we've seen in component technology through the years. And it's, you know, for what we like to think are the right reasons. And again, these things have been showing up in different ways, different places. There's dual inline packages like this small outline, no lead type device. This is probably the more traditional BTC with the pullback terminal metallization and various iterations that way. So pullback versus no pullback, this kind of gives you an idea of what we're talking about. So in a no pullback, of course, you've got kind of like an external, you can actually see part of the joint itself, whereas in a pullback terminal, it's a little bit off-center there. So inspection's a little bit more difficult to do. And this is one diagram of the joint cross-section. There's really not necessarily a gap here, but just gives you an idea. We're talking about the heel and toe of the joint and of this type of thing. And this is an actual cross-section of a QFN joint. So one of the advantages here we can see is, as I mentioned, there can be, to a certain degree, a bit of external examination, inspection of the part of the joint. Doesn't necessarily mean it's all there. You know, it's say an advantage over, say, an area array, unless of course using an endoscope. But it isn't necessarily, you know, it could be, if you don't see this forming, it could be symptomatic of a problem, but just because it's there doesn't necessarily mean that what's under here is all, you know, well and good. So these are just some of the things. This is from Vern Solberg in terms of some of the things with regard to pad design from a design for manufacturability standpoint. And again, you know, this is comparing, say, from a QFN to an SON type terminal, pullback and non-pullback and pullback, and just gives you some of the specs on it. Okay, so one of the biggest issues we hear about, and I'm sure a lot of you are doing about, is the center pad issues. Like, for the most part, within reason, if you're controlling a lot of things or your print height, things along those lines, generally the outer leads are not necessarily the problems. I mean, we do see some things resembling, like, you know, head and pillow and stuff like that occasionally. But one of the biggest concerns we hear about is the center pad issue. Either being too high and actually making the component float during reflow, and so we lose our alignment, or the other big concern are the voids that we're finding in it. People get very, very scared because we see a very high propensity of voids, typically in that very large you know, joint, if you will. So, you know, some of this gets back down to pad design, which we'll talk a little bit about, and some of the options with regard to printing the paste, getting the paste down. And this would be, you know, first of all, dealing with a paste, you want something that's well-defined and non-slumping paste. However, we see here in this print, yeah, we got good volume, which is ideal for the leads, but from a standpoint of putting this type of a mass down of solder there, that's really scary, because what's going to happen when we go to reflow. If you basically, you look at it almost like an excessive amount of paste, and one of the results you get is very large-scale voiding of that thermal pad. And it'll, as I'll show you, it'll actually present component float. And what you have is, as it reflows, it's basically lifting up almost dome-shaped, and therefore the QFN is literally lifted off the board. So the concept that we're using these days is what's called window painting. And there's all kinds of various forms, which I'll show you. But the idea is, rather than having that solid mass in your center ground plane, that we break it up into smaller masses. And that has two basic advantages. One, you're not creating that big giant mass that's creating a dome. The other thing you're allowing to do, or trying to, or approaching, is the idea that outgassing, allowing that outgassing from the flux to basically dissipate, because that's where the voids come from. What are voids typically? They're entrapped flux gases, and they have no place to go. So on that big mass, that's what you get. So the idea is, by having window painting, you have little routings, little canals, if you will, that some of the outgassing, plus you're using a slightly smaller volume, so you're introducing a smaller volume of flux with voiding anyway. That's it in theory, of course. So again, this is that doming effect that you get when you have that big solid mass here. But the idea about windowing or window painting, or we'll look at some of the different things, is the idea that you know, you basically are allowing a controlled outgassing. And by the way, there are all other schemes we've seen attempts on this, because it is a problem. But I will say this, in terms of voids, you still have to ask the fundamental question, because you're still going to get voids with this, you know, with regard to that center pad. You have to ask yourself, is the void a symptom or a defect? And that's the key thing. And that's true of any kind of solder joint where we have voids. Where is the void, or the amount of voids in this case? How effective are they? I believe there may be a spec. I'm not sure. I have to recall from that 7093. But in general, there's a certain amount of voiding that's been determined to be basically okay, because it's not unusual to see 50% voiding in these things. So the question is, remember, there's still enough solder mass there that's going to be making good contact and probably good heat dissipation. But really, the person to decide whether that voiding is acceptable, that would be the design engineer, the component engineer. Say, is there enough contact there for allow the heat dissipation? But most of the cases we've run across, and Greg might have some other data from the design for reliability standpoint, most of the cases we've seen, there's more than ample that it's not going to do it. But there's the aesthetic problem, good old cosmetics. And the idea is yeah, my customer might see it, things along those lines, and what do they see, all these voids, my God, it's a defective thing. And yeah, it happens. We had one client we were working with that were making onboard power supplies, or miniature power supply circuits, and they were using QFNs. And it is very likely that once these devices are on board the master board that the customer is putting them on, that they might indeed be X-rayed, and it would show up this voiding. They were very, very concerned about it. And we looked at a lot of different options for trying to reduce that voiding. Even though structurally, and from a thermal dissipation standpoint, it was fine. It was ample. It was cosmetics. You know, it's the old give me that shiny joint syndrome again. So typically people, there's a reduction taking place here, reducing that mass, and again, and kind of spreading it around a little bit. So typically we've seen as much as, I typically work with 50% reduction, but we've seen some cases where we've gone to as much as 80% reduction. And we've actually even printed dots over you know, capped thermal vias as well. But again, that could be questionable. Greg might have some comments on that. Typically talk about 50 micron thick solder joints, and that's going to help improve the board level reliability. And again, the type of recommendation for solder paste coverage, we're saying at least 50% for plug vias, 75% for encroached via types. And this is what we're talking about. We talk about window painting, things like that. So the idea here is, yeah, it looks like a window pane. And, but they could be dots, large dots, small dots, things along these lines. And this is, again, the relative coverage. So as you can see, this methodology has about 81% coverage. This one's actually down to 50% coverage. And the reduction therefore in that one, using these big dots, is 37% coverage. Again, I would dare say I can't recommend one over the other at this point in time, or maybe some of other speakers can. But generally, it's you do a design of experiment. You have to experiment with this type of thing, and definitely keep reading and abreast on what some of the research being done, because there's a lot of attention being given to this area. I'll also say that another thing that was experimented with, and we tried doing this, and Brooke may comment on this as well, is the idea of rather than using a solder paste, there was some experimentation done using solder preforms. And the theory there is in using these preforms, in other words, you put down perhaps a thin layer of solder paste, maybe a step down situation, or you don't put any down and you just pick and place these little preforms. Talk about the type of preforms that look like, that you get them on tape and reel. They're about the size of like 0805 or 1206. And the idea with preforms is preforms have a less volume of flux than solder paste does. So the idea, oh, that's good. We're reducing the amount of flux, less outgassing. And we spread those out, plus we can control where we're working them. There's been kind of mixed success. As I said, I think Brooke is going to comment on that later, because she's been privy to a lot of the experimentation that's been done with that. We tried it with one of my customers to a certain degree, but it was nothing conclusive. So other manufacturing reliability challenges, there's the manufacturability of it, compatibility with other processes, and reliability acceptance, and particularly long-lived severe environment. I'm going to touch on that. Greg will definitely get more into that. But one of the things I want to say is, in terms of with other processes that we're using, Bob presented the term disruptive technologies. One of the things we look for, from our standpoint in assembly, is I'm looking for concurrent process technologies. In other words, does this device fit into my process? Can I use my printer, my pick and place, my reflow, or do I have to do something different and strange? Okay. Examples. If you go back, and this is almost another near anachronism, except it's being used, it was something called tape automated packaging, or tab devices, way back when. And this was, again, I would say probably very late 80s, early 90s. And what these required a special machine that would place the chip in like a film type, a Kapton type package. You would do interlead bonding, either typically wire bond or sometimes thermal compression. And then it was excised from the tape carrier package, and that's another word, it's called tape carrier package. And this special machine center would place it on the board and typically use hot bar to reflow it to the board. This was a separate machine, typically about $250,000. It could not do your other pick and place. It was separate from your pick and place machine. But at the time, everybody was going, this is great, it's a high I/O. These tab packages or tape carrier packages are high I/O. They were typically like, I believe, a 12 mil pitch on the outer layer. And of course, we were killing ourselves with leading components with those pitches with coplanarity and collinearity process. So this was seen as the new, great hope. And, but again, part of the problem was it took the special machine, and companies built machines. Universal built them, Ismeca built them, they were out there. But then along came this readaptation of the area array, basically picked up from the old IBM concept by Motorola, and along came the ball grid array, and it kind of totally displaced this. Because the other limitation with the tape carrier package is you had to be doing a lot of volume of that same component to justify a separate machine center to do like that. So companies like Casio and Franklin, they were making the little, this is again before smartphones, making the little PDA type devices stuff. They could afford that, they could crank it out. Also Sun Micro liked the tape carrier package because for speed of the device. But ultimately, the ball grid array was wonderful. Why? Because the ball grid array didn't require a special machine. It used the same pick and place, maybe some modifications for vision, same reflow, same printer. Okay, concurrent process technology. So that's one of the things we look for versus concurrent versus truly disruptive, or what's this going to cost me to do? So in some cases you have to adapt some of your equipment, but with the BTCs, basically it's, I would say, probably safely say anybody here with any equipment you're using are able to do BTCs, and with very little, if any, adaptation. So again, Greg's going to go more into this, but what we find is, in general, with packaging over the years, is the less standoff you have, generally in terms of thermal cycling, the reliability kind of declines. So when BGAs came out, they were compared to QFPs, and typically we saw something where say 40 to 125 C range, 3,000, 8,000 cycles. And compared to, say, over 10,000 with the leads, the QFPs, because leads give a certain degree of resilience. And that was a gold wing lead. Imagine with the J lead was even greater because the standoff was even greater. But we really didn't see J lead devices on below 50 mil pitch, so they kind of went by the wayside. But the gold wing, of course, is still in use. So very, very high resilience. So here we looked at the BGA and go, wow, there's a lot of applications where we see a lot of thermal cycling or high degree of thermal cycles. Maybe the BGA is not such a hot setup, or that area array. Under hood was one of the examples that go, oh, that's probably not a good idea. So we're limited by that. We get down to QFNs, which even less of a standoff. Really, your standoff is the actual solder paste, the solder deposit. So if you're printing 5 mil, you're talking about a standoff of what, about 2.5 mil. So it's even less. So as a result, its resistance to a thermal cycle is even less. So again, it's application driven. Is this a good idea for this type of application based on, for example, thermal cycling to use this device? That's not a decision we make on the manufacturing floor. That's made by obviously design and everything. But and this is again a Weibel of this is based on SAC versus tin lead. But again, we see thermal cycled, and again, even regardless of the solder that we're using here, that the BTCs generally go less there. Again, lead-free is as good as tin lead in 0 to 100, poor in 40 to 125. And the SAC solder joints under a zero test condition have, in this test, 3 point times longer characteristic life cycles than the under the 40 to 125 test conditions. In tin lead, it was 1.8 longer. So this is, again, what the crack formation typically looks like on a BTC from a thermal cycling. This is from the 0 to 100. So again, a higher silver alloys, for example, the particles promotes, because the higher volume of the silver tin particles promotes some more fatigue resistance, but still, there's a limitation in the application of this device. Again, another area is vibration reliability. Now here's the opposite. As opposed to thermal cycling, so far from a lot of studies we've seen from a vibration reliability, it's the best of any component we've seen out there. And call it a low center of gravity, the fact that that low standoff actually is acting in your favor, that it's close to the board. So it seems to work out really well that way. Here we have again, compared to say the BGAs, some of the other components, there's the QFN, there's a TQFP. So again, from an application standpoint, something seeing a lot of vibration, this might be a good thing. Another thing is, of course, again, very low profile. The idea of any warping of the board is going to be detrimental. So either before reflow or certainly post reflow. So I know Greg's going to comment this because this was a study basically done by DFR, and so I'll let him get more into that. But again, that's the other aspect. Again, we've much less to deal with here. By the way, from an assembly standpoint, I can't stress enough how important solder paste height and volume is. It's always been important. When area arrays came out, it became paramount. Absolutely, because, and in fact, in my experience, a lot of the problems we see with areas, assuming the board is designed right, is basically improper solder paste height. And you've got to do solder paste inspection. I can't stress it enough. It's one of my soapboxes, and it becomes even more imperative when we're dealing with bottom terminated components, because you have such a little to deal with there. And that solder paste height is everything. So we're seeing more and more I mean, the idea of solder paste inspection, people are very resistant to the whole concept for years. How many people are doing post print inspection, solder paste inspection? Outstanding. Oh, that makes it, because a few years ago, it would only maybe 6 years ago, you might see one hand go up very shyly too. So, and there's a lot of, much more of a nice array of equipment available for doing it. A lot of the people, the companies that make that stuff have gotten on board with it. There's more and more equipment in the range, from tabletop to the high-end machines. It's amazing where it's gone, and the equipment's getting better and better. And I mean, I feel strongly enough about this that if I had a capital purchase to make, and my choice was between SPI and AOI, I would go for SPI first. And this is one of the reasons, because your AOI is not going to see that. It's not going to see your ball grid array joints. It's certainly not going to see your QFN joints. So get it right in the first place. Catch it at printing before things get more expensive. So, okay, off my soapbox now. And again, area array devices are known to have board flexure limitations. Exactly for example, the SAC alloy attached to the maximum microstrain can be as low as 500. And QFNs have even a lower level of compliance, and therefore may be more susceptible to flux-induced joint and laminate cracks, since these areas are basically induced the most strain. So where do we see this? We see it in circuit tests. These are the traditional areas in circuit tests, bed of nail fixtures. Depaneling processes, oh, these are among the biggest killers. Amazing. I mean, they have it traditionally anyway. You know, again, observing clearances, there are design guidelines, particularly since most people here are probably using pizza cutters. Come on, admit it. We see all the time. You have to keep a certain proximity from where your scoring is, where you're cutting it from devices like ceramic capacitors and these guys as well. And I mean, routing is probably the best way to go, but we know it's not always practical. So observe your design guidelines. And I believe typically, I know for ceramic capacitors it's about a minimum of 5 millimeters. These are probably even a little bit more. In any hand assembly operations, particularly of gorillas or that fellow, the Hulk that Bob had to slide on your assembly line. So this is another area that really has whacked BTCs more than in many respects other components we've seen. And this is conformal coating. And what happens is you apply the conformal coating, it seeps under the device when it's being applied. And unbeknownst to a lot of people, that conformal coatings have a very high coefficient of expansion, particularly in the z-axis, in the vertical axis. So what will happen is, as this stuff sets out there, cures and everything else, it's acting as a force pushing up on it. And now it may not be instantaneous failure. It may be, even if you're doing burn-in and thermal cycling, it may be further on. And again, I believe Greg might comment on this. I'm really setting you up for a lot, Greg. It's pretty good. Damn, take it, Greg. But anyway, but we've had a number of cases where this was it. One that comes to mind immediately was about a year and a half ago. It was a company in the United States making power meters with the RF signal, so the power guy doesn't have to drive up your driveway. He gets it by doing a drive-by. And they were having occasional failures of their devices, and it was traced down to this area, this particular BTC. And the thing was, it was typically 6 months in the field. And it wasn't, and remember, these things are sitting in different environments, extreme cold, extreme heat, medium, and it was all over the spectrum. So it wasn't like, oh, it was the ones that were very, very cold. And these guys were doing very good due diligence on their burn-in and everything else. To complicate it even further, not only were they conformal coating in the area of the BTC, they were not using the ground plane of the BTC. They were not soldering the ground plane of the BTC. So there was this conformal coating goes totally under that ground plane. So there was no solder. I mean, you talk about zero, ultimate reduction. So this stuff over time, they didn't see it in burn-in, but after it got out in the field, all that thermal expansion and contraction stuff eventually pushed it up. And they were getting broken circuits. So it's conformal coating that be very, very careful with. And so again, you could say that conformal coating basically reduces reliability. And this is, again, when it flows under the component and expands during the thermal cycle. Again, the reasons for voiding under BTCs, you have a very large area of thermal pad, you have a large paste volume. And the more flux, the more paste, the more flux, the more outgassing. And you have a very low standoff. So as far as the stuff going somewhere, as opposed to if you have an area array, a bulk grid array, it's got some area to kind of, steam to vent, if you will. So our low standoff really prevents it. And then if you have a large number of thermal vias, remember thermal vias are also acting, if you will, as heat ducts, so not necessarily helping the dissipation. So again, generally for the large center pad, the typical voiding criteria would be you want to see less than 50%. I don't believe this is again, you guys can correct me, I don't believe it's a standard. It's just a, empirical rule of thumb that you want to see. And that may be disproved as time goes by, particularly, again, by people involved in the reliability testing area. And thermal dissipation typically requires lower voiding, under 30. So it really depends on the application device, what it's seeing, things along those lines. But again, determining whether a void is a symptom or a defect, and that's true, as I said, of any voiding in any kind of component, any kind of lead. So it's going to affect the mechanical properties of the joints, of course, strength, ductility, creep, and fatigue life. And so, voids are there, but we have to know, how much it's affecting under those conditions. And to really know, that's when you basically do a DOE with somebody like DFR. Has a nice ring to it. And voids could also produce spot overheating too, and therefore lessening the reliability of the solder joints. So again, voiding versus window pane, it just shows that, again, from going to a window pane versus a solid mass, that we're affecting our voiding considerably. So again, we're going to see more and more experimentation that way. And that's what this voiding typically looks like. And those of you who've done BTCs, you know, oh yeah, that looks real familiar, yep. So even with the pad window painting, you're going to get voids. And the other thing also is, okay, we're concentrating that, but don't neglect looking at, you know, what your solder joint reliability looks like on your pads too. Don't just focus on the center plane. Look at those pads because they're extremely important. And again, excessive voids can also cause coplanarity issues and obviously open joints. So again, right now it's stipulated again, not spec, 50% coverage criteria for the thermal pad. And this is just an example of some of the voiding mechanisms. And I think Brooke's going to probably be going into this more so. But again, it's trapped flux gassing, not being able to get out, and it forms these bubbles or voids. And it's typical what it is elsewhere when we have via pads and things like that. Here's voiding in a QFN due to an unfilled via in pad. So again, that exasperates the situation as well, compared to what else we might also have. So again, other pad reduction, reducing the ground plane pad in the center by using a grid pad or window painting, the smaller pads, in order to break it up. And masking off allows some outgassing between the pads under the component as well. And as I said, we've seen some other exotic things being done where people have actually scored little canals, if you will, in the board itself to kind of allow to aid the outgassing, give it a little bit more room to vent out there. And I have no idea what that costs from a board fabrication standpoint. I hate to think about it, you know, plus some of the limitations in design and everything. But we're learning about this, and we're trying to get better. Again, also looking at voiding versus stencil thickness. Again, going down, of course, reducing the thickness of the solder and the volume of the solder, of course, is going to result in less flux volume and less flux outgassing. But again, that may not be practical with regard to your application and the rest of the joint. And then this was also, we've been looking at the reflow profile and different effects on the profile, particularly working with the soak or pre-flow zone, peak temperature, and the time above liquidus. So one of the things we've seen is that with a longer time above liquidus, we actually see voiding go down a little bit. But again, what are the consequences that way with regard to your intermetallic formation? So what are the trade-offs here and there? It's never easy, is it? And again, the longer the soak and the higher the peak temperature, all things that from a practical standpoint and you know, we're trying to avoid, it obviously helps reduce the voiding. So again, how important is that? What level of voiding do you have? How much do you sacrifice on the other end? How much can you sacrifice before it starts getting dangerous? So again, voids, is it how symptomatic or how defective are they? So no clean residue issues. I know Brooke will be talking about this. Again, part of the problem is solvents can escape. The residues may not be safe, even though you have the full time temperature exposure and you've basically treated the flux exactly we wanted to see. There still may be some volatile materials in there, and that's the whole thing. So basically, some of the philosophy here is that because you may have some of the fluxes that are not benign, that a lot of people using BTCs are cleaning and doing cleaning. And of course, that's another challenge because that low clearance, you know, how we get under there. So typically we're seeing a lot of cleaning using saponifiers, you know, mixture, because the saponifier improves the surface tension of the water to actually get in there as opposed to using just straight aqueous. Even in cases where we've seen people using a aqueous water-based flux. So again, when the flux is activated, it fully volatiles, and it's supposed to leave a benign residue. That's what no clean's all about, with no impact. But when the solvent is not allowed to release, again, that flux residue and that gas is conductive and moisture absorbing. And we found product in the field for 9 months that still have gooey conductive flux causing performance problems. In other words, it hasn't quite totally caramelized. And so here again, and I believe Eric's going to be talking about probably the cleaning issues as well too, no clean versus cleaning, things along those lines. So again, the idea that here's an example, prior to reflow, QFN with paste, here's from a 5 mil stencil. So after reflow, We see the QFN is pulled down to 2 mils off the board, to 2.5 mils. Board surface with trap gooey flux between the leads and the ground plane. It's this stuff right here. And that gooey means it's volatile. Again, other issues I know Eric will get into that we're doing with the low clearance. Same old issues in that large center pad. So you have a high pace, high flux volume. How do you maintain a cleaning path, flow path? What are some of the ways and means of doing that? Inspection issues, well, again, just like with BJs, unless Superman's working on your line, you need X-ray. And AOI is very difficult. Where we have the non-pullback, we actually have some semblance of lead form. You may be able to inspect it, some of the machines. Of course, manually is very, very difficult, especially if there's no vertical wetting present in the where you have the pullback. Endoscope, just like with a BGA, it's good for the edge viewing, and typically these are perimeter. So, but you know, how much can you see underneath? There's a limitation. And again, X-ray is good for voiding, bridges, wetting, and it's probably the only method for looking at the center pad. So again, this is some of the inspection criteria from the IPC for BTC type components. And again, poor side fillets, poor wetting in the corner joint. We've seen that happen. And the other thing also to be aware, as always with any of these devices, I'm not saying that's an example of a popcorn effect, but also beware of the popcorn effect. MSD is still an issue with these devices. Again, they're smaller, thinner, you know, typical. So be very aware of the moisture sensitivity limit, level of these devices, and have your program in order when you're dealing with them. Here's X-ray inspection, good, bad comparison. So up there we see, you know, again, minimal voiding. Here we see a lot of voiding. And then here we have in the actual leads, different degrees of voiding. So you have the good, the bad, and the ugly. And excessive solder, you know, and this was X-ray, virtual X-ray cross-sectioning. And just taking a look here at, again, some of the excess solder, what you're getting. So it is possible to have too much solder in these. But again, I'll let Greg comment on reliability aspects. Yes?
When you're talking about X-ray, how would you compare X-ray, say, to fluoroscopy as an inspection tool?
Ooh, that's a good one, fluoroscopy. I don't know. I haven't had personally enough experience with fluoroscopy in these applications. That's an interesting. I know it's been used.
The reason I ask that
yeah.
is typically X-ray, you get one shot.
Right.
Okay, and then you have to develop. Whereas fluoroscopy, you can actually take live shots and leave that tube running.
Right.
Keep inspecting, which would, I would think would make that very simple.
Very interesting. Greg, have you seen anybody really use it? No. Eric, have you encountered anybody? We just don't see a lot of fluoroscopy equipment in our field. I think that's part of it. Like, not yet. Exactly. Well, you may be exactly right. It may be the new hot setup. Again, as you're saying, because you get to do things in real time. So it may be. It's very interesting, though. I'm glad you brought it up. Anyway, we get into rework issues. Again, you're dealing with a large ground plane, so trying to heat that, and I'll leave that to the experts on rework, and guys talking about that. But you're dealing with a very large ground plane, so heating that, and then again lift off of the large vertical surface tension, you know, from the middle versus the the ground plane versus the outer counts, and again reprinting the paste as always with any kind of device like area arrays and such. So one approach is to do the actual paste printing on the component for rework rather than trying to do a micro stencil on the board. I don't know, I'll let you guys comment on that and the applications on that. You guys are the experts on the rework. But again, in summary, they're not going to go away. We're seeing increasing usage. The size is going to go down, and so is the cost. And they're very, very accepted for the reasons we outlined before. And again, the biggest issue, one of the biggest issues, the paste printing on the center pad issue. And again, as I said, determining from your application, from all aspects of it, doing a proper DOE, whether it's a symptom or a defect. And again, typically we're going to see a lot of V-in pad on these type of devices just because of the nature of them. X-ray is basically required for inspection, although fluoroscopy is very interesting. I'm going to ponder that. I like that. And cleaning, again, we said it may be required. Eric will be talking more about that. But again, the challenges because of the low clearance. And that's what I wanted to say. And again, don't be afraid of it. You're not afraid. As I said, as far as disruptive and components, you know, these have been around for a while, but to a lot of you, they're new, they're scary. Don't be intimidated, don't be afraid. And especially after that, you're going to get some really good information from all around. You'll be walking away a lot better off. But understand that back around 1990, 91, people were afraid of ball grid arrays. And my God, what are we going to deal with this? And there were people capitalizing. I can remember certain people out there, a certain consultant here and there making it sound like, oh, forget everything you know. You got to totally relearn all about surface mount to do BGAs. Totally untrue. I mean, it was great. What I said, it was a concurrent process technology. It was practically plug-in. It was wonderful. You didn't have to relearn everything. They were just trying to, it's like a remake of a movie and then throwing new actors in or something. So I wrote an article. Back then I was writing for Circuits Assembly magazine, and I decided to dispute that and say, no, we can deal with these. We can do it. And I wrote an article, and I called it, What's the BFD About BGAs? And understand, my editor, Ron, goes, I like it. Well, there was a little footnote. BFD stood for Befuddling Fundamental Dilemma. I don't know what you guys thought it stood for. But you can find it archived on our website. But it was a very popular article. At least people read it because of the name. But the whole idea was that we learn about these, we deal with these, and we can surmount the problems. So certainly that's the case with bottom terminated components.